Hello, everyone. My name is Calvin Carpenter, and this is homework 3 for computational methods. In this homework, we're going to be dealing with distillation. So here, let me just kind of describe the basis of what's going on here. Here's our, actually, I'm going to draw that a little different. So pretend this is our tower. Okay. Yeah, pretend this is our tower, and you have some sort of liquid flowing across each stage. What's going on here is you have a feed. And that feed is being both. So it's coming in contact with liquid and vapor. So you have, shoot. Probably should have drew this beforehand. Okay, so basically you have a feed and you're trying to separate components, and you have an equilibrium of vapor and liquid inside of this column. And so with these arrows, vapor is rising to the top and liquid's falling to the bottom. And so you have stripping and rectifying. And so basically the liquid is pulling components out of the vapor, and then the vapor is pulling components out of the liquid. And there's certain duties, usually in MMBTU, on each the reboiler and the condenser, to ensure some sort of purity within your product so you can get good separation. So in this line, you have your distillate. This line, you have your bottoms. And basically, we're going to look into basically these molar compositions, or the equilibrium of vapor and liquid compositions with constant relative volatility, as I stated here. So that's the first thing we're going to do. Okay. So we have X times our relative volatility over minus X. And then we have our Y over 1 minus Y. So that's going to be our balance. It's going to be our vapor-liquid balance here, or equilibrium. So we're going to try and isolate Y. So if we multiply out 1 minus Y, then we can multiply our X alpha term throughout that with X alpha over 1 minus X minus Y times X alpha over 1 minus X equals Y. And then we can move the term to the other side. So x alpha over 1 minus x equals y plus y times x alpha over 1 minus x. That's going to be equal to y times 1 plus x alpha over 1 minus x. And then we want to put all the terms attached to the y in terms of 1 minus x. So we have, that's a little bit sloppy, x alpha over 1 minus x equals y times 1 minus x alpha over 1 minus x. And I just put this 1 in terms of 1 minus x over 1 minus x, and then added it to the term. Not, for some reason it's not updating. There it is. Okay. And that leaves us with, if we multiply that by the reciprocal to move it to the other side, then we end up getting x alpha over 1 minus x alpha is equal to y. And that's going to be our equilibrium vapor-liquid composition with constant relative volatility. All right. So now if we narrow our scope down to like one section of our distillation, let's just look at the feed stage. So we have this guy here. We have our feed. We have our feed. So we have some liquid in here, right? So we're going to have liquid entering and leaving, and then we have vapor entering and leaving. And so the liquid entering is going to be in terms of x, so it's going to be x I plus 1 li plus 1. And then leaving, it's going to be xi li. And then vapor, you're going to have sorry, not plus. Yi minus 1, Vi minus 1. And then on the outlet, you're going to have Yi Vi. So that'll be like your balance for each stage, and your stage is I. Okay. Now, if we want to draw out like the material balance for this, so we would have basically you're going to have xi, so you're going to have your stuff going in minus your stuff going out, right? So let's just start. Let's just include the feed for this one. So Fizi plus xi plus 1 li plus 1 plus y I minus 1 vi minus 1, and then you're going to subtract xi li and your yi vi. So that's your mole balance for your liquid and vapor fractions for stage I. And then this can be taken so this is going to be your mole fraction. This is going to be your total moles, and then measure the change of those in terms of time. Okay. Now, if we want to do the total moles for a stage, we just take our Li plus 1 plus Vi minus 1 plus Fi minus Li minus Vi. That'll be your total moles for the stage. Okay. Now, if we want to get, sorry, I should probably separate this, like a line or something. So now if we want to figure out what our change in xi in terms of time will be for that differential equation, we can apply the product rule to get another variation of this dmixi over dt. So dmixi over dt is equal to mi times dxi over dt plus xi times dmi over dt. That will be basically we can take, I don't know why it's not updating again. It's taking forever. Okay, there it is. Sorry if there's any delay. I'm writing this on my iPad and then trying to record it on my computer. But anyway, where was I? So we can take this guy. We're gonna plug that into here, and then we can rearrange it, and then divide by mi to isolate for dxi over dt. So basically, we're gonna have dmixi, and we're gonna do most of that in the code later on. But if we just visually isolate it now, we'll have minus xi dmi over dt divided by mi is equal to dxi over dt. And that will be our last of the differential equations we'll need to satisfy part A for this assignment. So we're done with part A, where we, as you can see here, we derived the equilibrium vapor composition given liquid composition for constant relative volatility. And that was with this y equals x alpha over 1 minus x alpha. And then we derived the dynamical equations for the molar holdup and compositions for non-feed and feed trays, reboiler and condenser, with these three equations here. So the next part, we're going to numerically solve the dynamical equations from part A to yield a steady state solution for reflux of 2. And then we're going to simulate an increase of the reflux to 10 over a time span of 200 seconds and make a plot of 6 different McCabe-Thiele diagrams showing how the composition of the column changes over time. So starting with the code, we're going to start with our inputs. So this section, I'm just going to label import necessary libraries from sources. So import numpy as np, and then Okay, so from Skype integrate, Skype.integrate import, I forget what that is. Did it solve? Is that it? Do you recognize that? Yeah, it did. Okay. And then from what we okay. Well, I think that's all the inputs we'll need. Well, we can always add more later on if we need to. So next, we are going to put in our relationship for our equilibrium relation using the relative volatility. So from our homework description over here, I forget where it says it right here. So assuming a constant relative volatility of 2, so we're going to set that. Sourcing it, we're going to set. I guess I'll call it A. A is equal to 2 dot. Okay, and then our x value, we're just setting the bounds for the 2 variables in this equation here. We're going to set our y value equal to the equation that we set up in the previous section. So it's going to be x times a, and then divided by 1 minus x times a. Okay, let's see if that works. Okay, so I just realized that I screwed this up from the last part. This should be plus. So I'm going to go ahead and fix that over here too. That's what it should be. So I apologize for that. All right, so now we have that figured out. We're going to create a plot for the equilibrium relationship. Gosh, I butchered that spelling. Okay, so first we're going to take fig equals make underscore subplots. Fig dot add underscore scatter. Okay, looks like I screwed something up here, making this plot. Okay, so this is just the width. We have to spell these out. Well, that looks very wrong. What did I screw up here? Okay, I think I know what I screwed up here. There we go. It was simply because this did not save when I hit Shift Enter for some reason. So, okay, that looks better. Okay, so the next step that we're going to do is set the column parameters from the homework description. So nt is equal to 6. That's going to be number of trays. and F equal to 3. It's going to be our feed tray. So then we have Weir underscore constant is equal to 2, I think. Oh, I forgot that we set that to 2. Just because we're just assuming the Weir constant is 2 right now. So F, and that's going to be our feed flow is equal to 1. So this is feed flow. Okay, so I guess we'll name this ZF. Is going to be 0.6. And that's our, I'll just copy and paste that. So ZF 0.6. And that's going to be this one right here. Okay, next is going to be U equals 0.5. It's going to be our feed liquid mole fraction. D equals 0.55. That's the distillate flow. And then next is going to be we'll set our reflux ratio next. So it's going to be R can be equal to 2. It's going to be set reflux ratio, and then okay. So I think now that we're on the topic of just like column things. So I guess we'll set the feed is equal to the bottoms okay, so now we can set our bottoms. That's going to be equal to our feed minus our distillate. So that's going to be F and D. And then our KC, which is right here, is going to be equal to 10. So molar holdup on tray, and let's set that variable equal to tray underscore m. Let's set that equal to 0. Where's that at? 0.1. Have our molar holdup on the tray. Now our reboiler is going to be a set point, and I'm pretty sure that's going to be 0.5. Yes. And then the condenser holdup is going to be 0.5 as well, but this one's just going to be set. It's not going to be like a set point like the reboiler is. So next we are going to set our vapor in the rectifying section, and that's going to be equal to R plus 1 in parentheses times our distillate. Next, we're going to have the vapor in the stripping section, and that's going to be V strip. And that's equal to V rec minus, in parentheses, 1 minus, did I capitalize Q? I did. 1 minus Q times the feed. So now, let me put a comment here. We're going to do rho concatenation for the liquid flow rates. L underscore initial is equal to MP dot R. I think that should be N, sorry, not M. Underscore. Sorry, that's not a normal parenthesis. There we go. V, comma, NP dot repeat. Yep. Plus B and F. So that'll repeat this for the amount of times that is NF. And then you close the parentheses, comma, NP dot repeat. So we're going to do another repetition of the rec. Let's see. And this one we're going to do for NF. Sorry, NT, which is number of trays, minus NF plus 1. Okay, we're going to close that out. Make sure that works. Okay, something's wrong with this one. Okay, it looks like we haven't defined V. I accidentally clicked V instead of B here. And that's for, wait, what in the world just happened? Why did it fill that? Does that work? Okay, cool. So now we have our row concatenation for the liquid flow rates. Next, we're going to do our row concatenation for the molar flow rates, condenser, and reboiler. And as I mentioned before, that's regarding these two sections right here from the diagram. So starting off, we'll have M underscore initial is equal to NP dot R as before, underscore we're going to take our reboiler set point, we're going to take our tray underscore M, which is 0.1 plus take our L underscore initial from our last row concatenation, take it from 1 to -1, and then divide by Weir underscore constant. Close that out. We're going to take that whole value, take that to the 2/3. And we're going to condenser underscore M, and then close everything out. Okay, so now we can set our T n is equal to 200 dot, and that is going to be our runtime for this little simulation we're going to be running. Okay, so shift enter. So next we are going to define the right hand side of the ODE, of our ordinary differential equation. Def okay, so we're going to define our right hand side in terms of T, vec, and capital R. So Vrec is equal to R plus 1 in parentheses times D. V strip is equal to Vrec minus 1 minus Q times our feed, then V is equal to NP dot R underscore open bracket NP dot repeat V strip comma NF. So we'll repeat V strip NF for the amount of NF times. NP repeat of Vrec plus 1 okay, and that's going to be our row concatenation for the total condenser. I'm going to put in the total condenser vapor flow rates. So let me copy and paste this in. So row concatenation for the total condenser vapor flow rates. Okay. Next, M comma X is equal to NP dot split okay, so that's setting M, our variables M and X into a split of with vector and 2. Y is equal to X times alpha divided by, in parentheses, 1 minus X, and then plus X times alpha, close parenthesis. And then dm is equal to np dot zeros like m. Dx is equal to np dot zeros like x. And then dmx is equal to the same thing that dm is equal to. Then L is equal to the same thing that dmx is equal to. L of -1 equal to R times D. So reflux times your distillate as we defined above. And L in brackets of 0 is equal to F minus D plus AC times parenthesis M bracket 0 minus Reboiler okay, so now that we have those initial conditions set, next we're going to set our total molar. I'm just going to say total moles. It's going to be our balance for our total moles. I'm just going to say total moles balance. Let's swap that. So we'll have L bracket 1 to -1 close bracket equal to Weir constant times M parenthesis wait I think it's actually parenthesis M bracket 1 to the -1 close bracket minus tray underscore M asterisk 5. Just in case I didn't make it clear before, that asterisk means you're doing like an exponential, and then close parenthesis. This parenthesis actually supposed to be right here, so that this whole value is raised to the 1.5. dm 1 to -1 is equal to v bracket colon -2 close bracket plus L 2 colon close bracket minus V 1 to -1 close bracket minus L 1 to -1, and then dmx of 1 to -1 is equal to y -2 times v brackets colon -2 plus x 2 colon times L 2 colon y 1 to -1 1 to -1 times L 1 to -1. So we have our dmx is going to be y to -2 times v to -2 plus x of 2 times L of 2 minus y of 1 to -1 times v of 1 to -1 minus x from 1 to -1 times L from 1 to -1. I think that looks about right. Now we're done with our total mole balance. So we're going to set up our feed conditions. I'm just going to say feed balance. So the M in brackets and F plus equals F dmx in brackets NF ZF times F. Now that we have our feed balance, we're going to set up our Molar conditions for the, they're not conditions, I meant to say compositions for the condenser operation. So first we have the M -1 equal to V of -2 minus L of -1 minus D dmx of 1 is equal to y of -2 times V of -2 minus x of -1 times L of -1 minus x of -1 times our distillate D. Okay, so now that we have our molar compositions for our condenser operation, we can set up our molar compositions for our reboiler operation. That's going to start with dm 0 equal to L of 1 minus V of 0 minus L of 0, and then dmx of 0 equal to x of 1 times L of 1 minus y of 0 times v of 0 minus x of 0 times L of 0. And finally, our dx is going to be equal to dmx minus x times dm, and all of that over m. So finally, we're going to return mp.r underscore, forget if this is parentheses or brackets, it's brackets, dm, comma, dx. Enter. Okay, it looks like that worked. So all of this, we're just doing balances for the feed, the condenser, reboiler, just based on like molar compositions at each stage. So for each part, you're going to have, like, as I mentioned before, like right here, you'll have an x times an L value going into the stage, and then an x and an L value going out of the stage, a y and a v value going into the stage, and then a y and a v value going out of the stage. So that's why you see like x times L and y times v for each specific section within the distillation tower. So that's what all of this means. So after we're done with that, next we're going to move on. Now we're going to solve the ODE for the reflux ratio of 2. So RES equals solve underscore solve IVP. And lowercase t, comma, v, colon, space, and then in parentheses, t, comma, v, comma, 2. So I think this should be capitalized. Wait, hold on, let me make sure this is right. Sorry, guys, this is... I just want to make sure I got this. No, it's not right. Okay, so RHS T, comma V, comma 2. Okay. Okay, 0, comma T end, close parenthesis, and then our initial Y value, which is P dot R underscore and initial, comma, and P dot repeat. In parentheses, Z, set ZF, comma, NT. I think my NT is capitalized, plus 2, close parenthesis, close brackets. Let me make sure that works. Let me make sure that works. Okay, comma. Method. RADAU in print in apostrophes, comma, dense output is equal to true. It looks like we have an error here. It says ZF is not defined. I swear I defined ZF. Oh, it's just capital Z. Oopsies. Still not good. It says true is not defined. I think that's supposed to be in quotations. Why is it saying true not defined? Okay, so I think that worked. That still didn't work. Very confused. It says ZF is not defined, but it's not. Lowercase ZF. Did I screw it up here? Somewhere? So I screwed it up right here. There we go. Now it works. Sorry about that, folks. So T plot is equal to np dot linspace np linspace 0 comma t end comma 101. Okay. Then m comma s dot sol T plot close parenthesis in nt plus 2 comma 1 close parenthesis big equals make underscore subplots open parenthesis rows equals 1 calls comma calls equals 2. Okay. Okay, I think that's all we need for that. So now we're going to create plots for compositions of molar holdups. For I in range, and t plus 2 colon big dot add underscore scatter. Accidentally typed fin. Okay. X equals t plot comma y is equal to x of 1 row equals 1 comma call is equal to 1. Name equals f apostrophe x so f is going to be of x in the fancy parenthesis of I. Okay. know why this isn't tan. I know why the I isn't tan. Try it again. X, I, apostrophe. Interesting. This should be tan, but it's not. F apostrophe X, I apostrophe. I'm not sure. I guess we'll roll with it and see what happens. Okay. Take that add underscore scatter. X equals T plot, comma, Y equals bracket I, 0 equals 1, column equal to 2. Close bracket, close parenthesis. Wait, I think I should have closed this bracket. Wait, why is okay? Fig update layout. Height is equal to 500. I think that'll do the job. Dark. That did not do it. Okay, I think I was supposed to do this here. Why did it do that? Okay, that worked. Next, we are going to all right, so this figure was not showing up because this is inside the for loop, and I realized that I included the M here, but I did not include it here. So M, now let's take a look. That does not look right. Okay, so this is supposed to be I. That should do it. Okay, so these are our plots for compositions of molar holdups with the reflux ratio of 2. And then we are going to be able to compare this to the plots of the reflux ratio of 10. But for now, we're going to do the McCabe-Thiele diagrams for reflux ratio of 2. So MCX is equal to X colon, comma, -1, close bracket. Sure. MCY equals MCX times alpha divided by, in parentheses, 1 minus MCX plus MCX times alpha, close parenthesis, enter. MCX equals NP dot repeat MCX comma 2 each in parentheses MCY comma 2. If you didn't notice, if you pick up on it, this equation here, that MCX times A over the 1 minus, that's still our equation that we derived here from part A. So moving on, MCY 1 colon close bracket is equal to MCY colon -1 MC, I think, is equal to NP dot C underscore MCX comma MCY close bracket MC 0 comma 1 close bracket is equal to MC open bracket 0 comma 0 close bracket C MC open bracket. Okay. We set our alpha value to 2. Why is it doing NP dot then space 0 1 100. EQY is equal to EQX times alpha divided by, in parentheses, 1 minus EQX plus EQX times alpha, close parentheses. Okay, and then fig equals make underscore subplots fig dot add scatter fig dot add underscore scatter x equal to EQX, y is equal to EQY. Okay. Fig dot add underscore scatter x equal to C colon 0 y is equal to MC colon comma mode defines 0 255 0. Okay, so that line we just did there, we put a note in here, number of stages. Next one we will do is rectifying and stripping sections. So fig dot add underscore scatter okay, and then y is equal to MC colon 2 comma 1 gonna copy and paste this. Mode is equal to lines, line color equals RGB 255, comma 0, comma 0. Big dot update underscore layout. Height 600 template. Okay, so this looks pretty right. Each one of these stair steps that you see here is indicative of a stage. So when I say number of stages, it means how many steps it takes to get through both the rectifying and stripping sections. So notice how these red lines have 2 different slopes. That's for each different section. And so the number of stages for this column, if you count up the steps, you'd have 1, 2, 3, 4, 5, 6. So 7 would be your number of stages for this McCabe-Thiele plot. So now we're going to test the ODE for the reflux ratio of 10. RES equals solve underscore IVP lambda P. Wait, I forget what I did here. V, yeah, P comma V colon. Yeah, I'm just going to copy and paste this from above, and then I'll have to replace that NPR. Okay, so RHS T comma V comma 10, and then we'll have 0 to T end, and then res dot y. Okay, and then method should be the same, radl. I don't know why it's underlined like that though. Hold on. Sorry, folks, give me 1 second. I'll make sure this is right. Yeah, I did something wrong. So solve underscore IVP equals, no, sorry, res equals solve underscore IVP, open parenthesis, lambda T comma V colon RHS, open parenthesis T comma V comma 10, should be the same as above, and then 0 to T end, and then res dot y, open bracket, colon comma -1, close bracket, comma method equals radl, comma dense output equals true. Oh shoot, that's okay. That's where I went wrong. Okay, we got it now. Sorry for that little delay, folks. N times equals to 101. Plot equals NP dot lim space and comma n times res dot sol two comma nt plus 2 comma -1 fig equals make underscore subplots rows equals 1 calls equals 2. And we're gonna plot the what do you call it? I'm going to call it RR reflux ratio 10. What do we call it? It was the compositions of molar holdups. Compositions of molar holdups. For I in range T plus 2. Dot add underscore scatter. We can go up here and we're just going to steal this. We're going to commit thievery. Just going to steal that. And it should just work, theoretically. That does not look right. Okay, so I'm just going to rerun all of it, see if that works. Oh, okay, that worked. So this is what it should look like. And in comparison to the reflux ratio of 2, you can see that a lot of them have an upward slope instantaneously instead of looking like this. And with this chart, we have a little bit of different plots as well. So now we are going to go ahead and do the McCabe-Thiele diagrams for a reflux ratio of 10. Okay. So n rows equals 2, and then calls equals 3. So it's going to be a 2 by 3 with number of plots. So fig 2 equals make underscore subplots. Rows equals n rows. Calls equals n calls. T, wait. Okay, so next T index underscore C. I'm gonna do T underscore index times divided by n rows times n calls. Rows times n calls, colon, plot underscore row is equal to, wait, plot underscore row is equal to I calls plus 1. Plot underscore call is equal to I percent n calls plus 1. T underscore index. The index inc times I. X equals X. Colon, comma, T underscore index. Okay. And then MCY is equal to alpha MCX divided by, in parentheses, 1 minus MCX plus MCX times alpha. Okay. And then MCX NP dot repeat is equal to NP dot repeat in parentheses MCX comma 2 MCY equals NP dot repeat MCY comma 2 MCY 1 close bracket is equal to MCY. Okay. MC is equal to NP dot C underscore MCX MCY 0, 1 equal to C 0, 0. C is equal to MC is equal to bracket colon -1. MC, yeah, MC bracket -1. Alpha is equal to 2 period. X equals NP dot lin space. NP dot lin space of from 0 to 1 with 100 steps. And then EQ y is equal to EQX times alpha divided by in parentheses 1 minus EQX times, plus EQX times alpha. If you notice, we've been using the same equation. You see it here, it's all just this equation. Okay. Next is big do dot add underscore scatter. This is equal to EQX EQY. Those lines, as always. Row is equal to plot underscore row, and then call equal to plot underscore call. So now I'm going to steal I'm going to steal the fig add scatter. I'm going to change it to 2. So I'll add it here. It's actually going to be tabbed over. Okay, so this is going to be stripping. No, sorry. This is going to be number of stages. And then change these to 2. Okay. Put that in for both. Big 2 dot update layout width equals 900 this time, so they all fit. Keep it 600. Keep the template the same. I guess we'll get rid of the legend this time because it'll be taking up space. Okay. Let's see here. We got. Okay, so this is what we got here. I'm gonna make it a little bigger. Do maybe 100 by 1,000. There we go. Now we can see. So these are the McCabe-Deal diagrams for the reflux ratio of 10. Once again, you can see the number of stages indicated by the green stair steps, and then the stripping and rectifying sections defined by the red lines here, and then the equilibrium curves is the different colored lines that was calculated by this y equals function over here. But other than that, this is all that we needed for part B of this assignment. So I hope you enjoyed. I hope you learned something. Thanks for watching.